Welcome to Orbit Observer. Settle in. Let the lights go low, let your shoulders drop away from your ears, and let your breathing slow down to match the pace of my voice, because tonight we are going somewhere very far away, and we are going there very, very slowly. There is no hurry here. Nothing we visit tonight is in any rush at all. The little world we are going to spend the next while with has been drifting through the dark for 4.5 billion years, and it will keep drifting long after this video ends, so there is truly nothing you need to stay awake for. You can let go whenever you like. I will keep talking softly, and the comet will keep turning quietly, whether you are here for all of it or whether you slip away somewhere in the middle. Either way is perfectly fine. So let me tell you about a comet shaped like a rubber duck. I want you to imagine, first, just how gentle this place is. Imagine standing on it. It is a small world, only about 4 kilometers from end to end, which means the whole thing would fit comfortably inside a single city. You could, in theory, walk from one side of it to the other in an afternoon if you walked slowly, and there is no other way to move here except slowly. Because the gravity is so faint, so astonishingly, impossibly faint. On Earth, when you jump, the ground pulls you straight back down before you have even finished the thought of jumping. Here, it does not. Here, if you crouched down and pushed off with your legs the way you would to hop over a small puddle, you would not come back down. You would simply keep going, up and away, off the surface entirely, out into the black, and you would never fall back. The pull of this comet is so weak that the speed you need to escape it forever is only about 1 meter per second. 1 meter per second. That is slower than a gentle walking pace. It is roughly the speed you move when you are wandering across a quiet room, half asleep already, reaching for the light switch. At that speed, on this comet, you would drift away like a balloon slipping out of an open hand, growing smaller and smaller against the stars until you were gone. So we will not jump. We will stay. We will keep our feet on the dark ground and let the little world carry us. And it is dark. I mean that quite precisely. This comet is darker than charcoal. If you have ever held a piece of coal or looked into the black heart of a dead fire the morning after, you have some sense of it, but the truth is even deeper than that. The surface of this comet reflects only about 6% of the light that touches it. 6%. Almost everything else, all that sunlight that has travelled so far to reach it, simply vanishes into the surface and does not come back out. It is one of the darkest objects in the entire solar system. A coal-black snowball drifting in the endless night, swallowing nearly all the light that finds it. If you were floating beside it and the sun were behind you, you would see not a bright shining thing but a shadow given shape, a hole cut into the field of stars, a soft black silhouette that you could only really see because of the stars it blotted out. That is the shape we are travelling toward tonight. A gentle darkness, 4 kilometers wide, turning slowly in the cold. Now here is a strange and lovely thing about this dark little world. For all its size, for all those 4 kilometers of black rock and ice, it barely weighs anything at all. Not by the standards of worlds. It is so light, in fact, that if you could somehow find an ocean large enough to hold it, the whole comet would float. It would bob on the surface like a cork, like a child's toy in the bath, because its density is only about half that of water. Half. Think of what that means. Water is not a heavy thing. And yet this comet, made of rock and dust and ancient ice, is only half as dense as the water in your glass on the bedside table. The reason is that it is mostly nothing. Mostly empty space. Roughly 3/4 of this comet is simply hollow, a honeycomb of gaps and pockets and voids, a frozen sponge of a world, fluffy and fragile and full of holes we cannot see from the outside. So although the whole thing weighs something like 10 billion tonnes, which sounds enormous, which is enormous by any human measure, it is feather light for its size. It is the lightest 4-kilometer world you could imagine, a vast, soft, dark thing, held together loosely, drifting so gently through space that it seems almost to have been made for the purpose of calm. And its shape. Its shape is the reason it has a name in 1,000 living rooms, the reason people who have never read a word about space still know it when they see it. Because this comet is shaped like a rubber duck. When the spacecraft that travelled all those years to meet it finally drew close enough in the year 2014, and its camera, an instrument called Osiris, sent back the first sharp pictures, everyone who saw them thought the same thing at the same moment. There, hanging in the dark, was a bath toy, a rounded lower part like a duck's plump body, and a smaller rounded part above it, like a duck's tilted head, and between them a narrow, pinched section, like the place where a duck's neck would be. It was unmistakable. Nobody had to be told what it looked like. The nickname arrived on its own, instantly, all around the world. The duck. And once you have seen it, you cannot unsee it. A 4-kilometer rubber duck, coal-black and light as a sponge, turning slowly in the endless night. But here is the part that most people never hear, and it is, I think, the most tender fact in this whole tender story. The duck is not one thing. The duck is two. For a long time, when scientists first saw that shape, that body and that head joined at the neck, one of the great questions was simple. Was this always one object, one lump of rock and ice that had been carved by time and sunlight into a shape that happened to resemble a duck? Or was it something else? And the answer, worked out carefully by a scientist named Massaroni and his colleagues, and published in the year 2015 in the journal Nature, was that the duck is two separate ancient bodies that came together and became one. It is what scientists call a contact binary. Two worlds, born apart, that found each other in the dark, and gently, fused. The way they knew this is quiet and beautiful. When they looked closely at the layers inside the comet, they found that the body and the head each have their own internal structure. Like the layers of an onion, curved sheets of material stacked one on top of another, built up over long ages. And crucially, the layers in the body run one way, following their own curve, and the layers in the head run a different way, following theirs. Two separate sets of onion layers, each complete, each obeying its own quiet logic. If the comet had been one object all along, the layers would flow smoothly through the whole thing, wrapping around it as a single form. They do not. There are two centers here, two hearts, two independent worlds that once formed on their own, far apart, long ago, before the planets were even finished, and then, across the enormous patience of deep time, drifted toward one another and touched. And the touch. I want you to really let this settle, because it is the softest collision imaginable. When these two ancient bodies met, they did not crash, they did not shatter, there was no violence in it at all. They came together at a walking pace, a crawl, so slowly, so gently, that neither one broke, that neither one so much as cracked from the meeting. It was less a collision than a settling. Two things that had wandered the dark separately, easing together over the ages, coming to rest against one another and simply staying. Neither shattered the other. They just leaned close, and merged, and became a single body drifting on through space, carrying inside itself the memory of having once been two. It is, when you think about it, one of the most peaceful events the universe has ever arranged. Two worlds meeting so softly that they did not wound each other at all. They just became the duck. That is where we are going tonight. To a place that was made by gentleness. Before we go any further, let me just say, quietly, that I would love to know where in the world you are drifting off from tonight. If you feel like it, whenever you're comfortable, tell me in the comments where you are, what part of the world, what kind of night it is outside your window. I read them, and there is something lovely about all these different places, all these different beds and dark rooms. Listening to the same slow story about the same little duck in space. And if you are new here, if you've only just found this quiet corner of the internet, you're very welcome to stay a while. You can subscribe if you'd like more nights like this one, more slow journeys to strange and gentle places, told softly, made for exactly this hour when the day is finally letting go of you. But there's no pressure at all. Mostly, I just want you to rest. So let's go back to the duck. Now, this little world was found by accident. That, too, feels right, somehow, for a comet made by two things drifting together by chance. It was not hunted down. It was not the goal of some grand search. It simply turned up, quietly, at the edge of a photograph of something else entirely. The year was 1969. At an observatory in a place called Alma-Ata in Kazakhstan, an astronomer named Klim Churyumov was studying a photographic plate. In those days, this is how you looked at the sky. You took a glass plate coated with light-sensitive chemicals, and you pointed a telescope at some patch of the heavens, and you let the faint light of distant things slowly etch themselves onto the plate over long minutes, and then you developed it, and you had a picture of the sky, frozen and permanent, that you could study at your leisure. The plate Churyumov was looking at had been exposed by a colleague, an astronomer named Svetlana Gerasimenko, and it was a picture of a completely different comet. A comet with the name 32P, sometimes called Coma's soul. That was the object they were interested in. That was the thing the whole exercise had been about. But as Churyumov examined the plate, his eye caught something near the edge. A second smudge. A faint, unexpected blur of light out toward the border of the image where it had no business being. It was not the comet they were studying. It was something else. Something that had wandered into the frame while the plate soaked up the light, a stranger caught at the margin of a portrait meant for someone else. And that faint smudge at the edge of a picture of another comet turned out to be a whole new world, a previously unknown comet, glimpsed by chance because it happened to drift through the corner of a photograph on a night in 1969. And so it took both their names. That is what the long, gentle name of this comet means. Churyumov, who noticed the smudge, and Gerasimenko, who had taken the plate on which the smudge appeared. Both of them joined together in the name, the way the two lobes of the comet are joined at the neck. Churyumov-Gerasimenko. And the number in front, the 67, the reason it is called 67P. That simply marks it as the 67th comet ever confirmed to be periodic. Periodic meaning that it returns, that it comes back around again and again on a regular schedule rather than blazing through once and vanishing forever into the dark. The P is for periodic. The 67 is its place in the long list of comets we have watched come home. So its full designation, 67P Churyumov-Gerasimenko, holds within it both a number that tells you it is faithful that it returns, and two names that remember the two people who first caught its light. One who took the picture, and one who saw the stranger at its edge. Let me tell you a little about how it returns, because its journey around the sun is a slow and stately thing, exactly the sort of orbit to fall asleep alongside. This comet belongs to a family. It is what astronomers call a Jupiter family comet, which means that its path through the solar system is shaped and shepherded by the gravity of Jupiter, the giant planet, the largest of all the planets. A world so massive that its pull reaches out across enormous distances and gently herds the smaller wanderers into line. Long ago, this comet very likely came from much further out, from the cold outer reaches, but over time its repeated passes near mighty Jupiter bent its path and drew it inward, shortened its journey, tamed its wild orbit into something smaller and more regular. And so now, instead of the enormous thousand-year loops that some comets travel, this little duck runs a much cozier circuit, one it completes on a timescale a human being could actually live to see, again and again. Its year, the time it takes to go once around the sun, is about 6.5 of our years. 6.44 years, to be exact, though there is no need to hold the number too tightly. Just let it wash over you. Every 6.5 years, the comet completes one full loop and comes back around. And in the span of a single human lifetime, it makes this journey many, many times over. And what a journey it is! It does not stay at one comfortable distance from the sun. It swings inward and then outward in a long, slow-breathing motion. At its closest approach to the sun, the point astronomers call perihelion, it comes in to within about 186 million kilometers, drawing near to the warmth, in toward the orbit of Mars, where the sun grows large enough to touch it and stir it awake. And then it swings back out again, all the way out past the orbit of Jupiter to its farthest point, its aphelion, more than 850 million kilometers from the sun, out into the deep and bitter cold, where the sun is only a bright star among stars. And everything freezes, and the comet drifts silent and dark and dreaming, in and out, near the warmth of Mars, then far past Jupiter into the deep cold, near and far, warm and frozen. A slow 6.5-year breath, in and out, over and over, for as long as it has been running this tamed and gentle orbit. There is something almost like sleep in it, that long, slow breathing, that steady return, the way it swings out into the cold dark and then comes back, and swings out and comes back. And it has been doing this, in one form or another, for almost unimaginably long. Because this comet is old. Not old the way a mountain is old, or old the way an ancient tree is old the way the sun is old. This little duck is roughly 4.5 billion years old, which means it dates back to the very birth of the solar system, back to the time before the planets had finished forming. Back when the space around the young sun was full of dust and ice and drifting fragments that were slowly gathering themselves into worlds. Most of that early material got swept up. It got crushed into planets, or cooked by the heat of the forming sun, or churned and melted and transformed beyond all recognition, so that today, on the earth beneath us, almost nothing survives in its original state from those first days. Everything here has been remade over and over by heat and pressure and the long working of time. But not the comet. The comet was left out. It formed far from the sun, in the deep cold, and it stayed there, in the freezer, untouched. It is a leftover. A building block that was never used, a piece of the original material of the solar system that somehow escaped being melted or crushed or made into something else, and simply remained frozen and quiet for 4.5 billion years. It is very nearly as old as the sun itself, and it carries within it, preserved in its dark, cold body, the actual stuff of the beginning. The ingredients the planets were made from, kept in deep freeze, unchanged, all this time. When we go to the comet, we are not just visiting a strange rock in space. We are visiting the past. We are touching the raw material of the world, the leftover dough from the making of everything, still cold, still waiting, still drifting after all these billions of years. Isn't that a soft thought to hold as you sink deeper into your pillow? That out there, right now, in the dark, there is a small black duck-shaped world, made of two ancient bodies that touched so gently they never broke. As old as the sun, so light it would float on water, so weakly held together that you could jump off it and never come back. Breathing its slow 6.5-year breath in toward Mars and out past Jupiter, again and again faithfully returning, as it has since before the Earth was the Earth. Let me stay here a moment longer, in the deep cold, at the far point of its orbit, where the comet spends so much of its long life. Out there, past Jupiter, the sun is small. It is still the brightest thing in the sky, still the anchor around which everything turns, but it is small, a brilliant point rather than a warming disk, and its light is thin, and its heat is almost nothing. Out there, the comet is utterly still. There are no jets of gas, no glowing cloud around it, none of the drama that comets are famous for. Out there, it is simply a dark, frozen, sleeping thing, coasting through the black at the top of its long loop, slowing as it reaches the farthest point the way a ball slows at the very top of its arc, pausing, almost, in that cold, distant place, before beginning the long fall back toward the warmth again. It spends years like this. Years in the deep freeze, silent and inactive, just drifting, just turning slowly, just being old and dark and patient in the enormous quiet between the stars. And it does turn. Even out there, in the stillness, the comet is gently rotating, the way nearly everything in space rotates, a slow and steady spin it has carried since its formation. A day on the comet, one full turn, takes about 12.5 hours, which means its days are a little shorter than our own, and all through the long cold years, at the far edge of its orbit, it keeps turning, faithfully, patiently, bringing first one dark face, and then another around to point at the distant sun, though so far out there is barely any warmth in that light to feel. It just turns. In the silence, in the cold, a slow rotation, a slow orbit, a slow world, everything about it unhurried, everything about it gentle, everything about it patient beyond any human measure of patience. I find that I could rest there, in that image, quite happily. The dark duck, turning slowly at the far cold edge of its orbit, the tiny sun in the distance, the enormous quiet all around. But there is so much more to tell you, and the night is long, and we have all the time we need. Let me hold for a while the sheer strangeness and softness of the two lobes, because I want you to be able to picture the shape clearly as you drift, to hold the whole duck in your mind like a small dark object you could cup in your hands. There is the body, the larger of the two lobes, the plump, lower part of the duck, and it measures roughly 4.1 kilometers in one direction, 3.3 in another, and 1.8 through its depth. So it is not a sphere, not a neat round ball, but a rounded, irregular lump, longer than it is deep, the way a river stone is rounded but not perfectly round, worn into a soft and lopsided shape. And then, joined to it, there is the head. The smaller lobe, the tilted upper part, and it measures about 2.6 kilometers by 2.3 by 1.8. Smaller than the body, but not by so much, a substantial thing in its own right, its own little rounded world, its own set of onion layers curving around its own quiet center. And between them, joining the head to the body, there is the neck, the narrow, pinched waist of the duck, the place where the two ancient bodies came to rest against one another and fused. And even this neck, this small connecting bridge, has a name. Because the people who mapped this comet gave names to all its regions, and they chose, fittingly, given that the whole mission was steeped in the imagery of ancient Egypt, to name the regions after the gods and sacred places of the old Egyptian world. And so the neck, the place where the two lobes meet, is called Hapy, after the ancient Egyptian god of the flooding of the Nile, the god of the life-giving waters that rose each year and made the land fertile. Hapy, the neck of the duck. The joint between two worlds. But the neck holds a quiet secret, and it is a secret I will only begin to open tonight, because it is one of the gentle mysteries we will return to as the hours pass. Across the neck, across Hapy, there runs a crack. A fracture in the surface, more than 500 meters long, a long thin line etched across the narrowest part of the comet, right at the point where head and body join. It is, in a sense, a stress line, the place where the strain of turning, the strain of heating and cooling, as the comet swings in toward the sun and out again, is very slowly, very patiently, working at the join, working at the ancient weld where the two bodies fused. And so there is a question here, a soft and unhurried question, the kind that does not keep you awake, but rather drifts alongside you as you fall. If the crack keeps growing across the long, slow ages, over many more of those 6.5-year loops, then one day, far in the future, the neck might give way entirely, and the duck might come apart. The head and the body, which drifted together so gently 4.5 billion years ago and have travelled as one ever since, might separate again, might part ways at last, undoing that ancient, tender merger, becoming two once more. But not tonight, not for a very, very long time. The crack grows slowly, the way everything about this world happens slowly, and for now the duck is whole, head and body joined at the neck called Hapy, turning together in the dark. We will come back to that crack later, when the comet swings in toward the sun and things begin, very gently, to stir. For now let it be enough to know that the join is there, and the crack is there, and both are patient, and neither is in any hurry to change. So this is our world then. This is where we will spend the night. A small, dark, gentle comet, 4 kilometers of coal-black ice and dust, so porous it is 3/4 empty, so light it would float on water, so weakly held that a footstep could carry you off it forever. Two ancient bodies, each with its own onion heart, that met at a walking pace before the planets were finished forming and fused so softly that neither broke, joined at a neck named for a river god, wearing a slow-growing crack that may one day, far off, let them part again. Found by chance at the edge of a photograph in 1969, named for the two people who caught its light, faithful and returning, looping the sun every 6.5 years, in toward the warmth of Mars and out past the cold of Jupiter, over and over, as it has for 4.5 billion years, as old as the sun, a leftover fragment of the very beginning, kept frozen and unchanged in the deep dark all this time. And soon, though not yet, a small machine will come. A spacecraft will travel for 10 long years and 6 billion kilometers to reach this quiet duck, and it will bring with it a tiny lander, and together they will do things no machine had ever done before. But that is a story for a little further into the night, when you are deeper into your rest. For now, just hold the duck in your mind, dark and light and gentle and old, turning slowly, breathing its long, slow breath around the sun, waiting, patiently, the way it has always waited, for us to come and find it in the dark. Let your breathing match its turning. Slow, unhurried, in toward the warmth, out toward the cold, and back again. There is nowhere we need to be, and all the time in the world to get there. The comet is not going anywhere it has not always been going. And neither are you. You are simply here, in the dark, drifting alongside a small, black duck-shaped world that was made by two things touching gently 4.5 billion years ago and has been coasting quietly through the night ever since. Stay with me, or drift. Either is fine. The story goes on softly, and the little world keeps turning, and there is so much more still to tell. 10. That is the number of facts we have covered so far, in the gentlest of tellings, and there are 90 more still waiting in the dark ahead of you, each one small and true and quiet, each one a place to rest your mind for a moment before moving on to the next. And so we move on now, unhurried, the way the comet moves, the way the night moves, without urgency and without any destination except this one, deeper into the story and deeper into sleep. Let us look more closely at the shape of this world. Because when Rosetta finally drew near enough in the summer of 2014 to see what it had been chasing for a decade, the scientists in the control room went quiet for a moment. Not with disappointment. With something closer to recognition, the way you feel when you see something strange that nonetheless looks exactly right, as though it had been waiting to be seen all along and had known it would come to this. The comet was not a potato, not a lopsided ball, not the vague smudged oval that simple models had suggested it might be. It was a duck. Unmistakably, improbably, and rather wonderfully, a duck. Two rounded lobes, joined at a narrower waist, a larger body below, and a smaller head above, and between them a connecting neck that gives the whole thing its unmistakable silhouette. There is no polite or technical way to avoid the comparison. The scientists did not try to. They called it the duck, they still call it the duck, and the duck it will remain. The larger lobe, the body of the duck, measures roughly 4.1 kilometers long, 3.3 wide, and 1.8 tall. You can sit with that for a moment, because those numbers are easy to hear and harder to feel. Think of a city block, a moderately large one, the kind with a few tall buildings and a park at one end. That is roughly the right length. Now compress it, make it broader, round off the edges. Drain it of every window and tree and person, coat it in black, freeze everything inside it, and lift it into the dark of space, and you have something approaching the body of the duck. A place that has all the dimensions of a neighborhood and none of its noise. The smaller lobe, the head, measures roughly 2.6 kilometers long, 2.3 wide, and 1.8 tall. A little more compact, a little more rounded, the way a head should be in proportion to a body. And between them, the neck, the narrow connecting bridge that bears the Egyptian name Hapy. Hapy is the name of the god of the Nile's annual flooding, the inundation that ancient Egypt depended on entirely for its crops and its survival. It is a generous, life-bringing name for a narrow, vulnerable place. The people naming the regions of this comet followed a rule. Every region would bear the name of an ancient Egyptian deity or place, a thread running back through the whole Rosetta story to its own beginning, to the stone and the obelisk and the decoding of a lost language. And so the neck of the duck became Hapy, the giver of water, the sustainer of life. Even here at the far cold edge of the solar system, even on a chunk of ice and dark carbon turning in the void. Hapy is the narrowest part of the comet, the slenderest connection between the head and the body, and it is, in a structural sense, the part under the most strain. When the comet warms and spins and vents its gas, the forces of all that activity concentrate in the neck, pulling and tugging at the junction between two ancient things. And researchers examining Rosetta's images found something in the neck that was both expected and quietly sobering once you understood what it meant. A fracture. A crack running through the Hapy region, more than 500 meters long, a stress line worked into the comet's weakest point by the repeated warming and spinning of hundreds of orbits over billions of years. 500 meters. That is the length of 5 city blocks, or the distance a person might walk in a comfortable 6 or 7 minutes, or the distance from one end of a large harbour to the other. A crack of that size, running through a solid object, is not a hairline imperfection. It is a statement. It is the structure saying, quietly and without drama, that it is under pressure, it may not hold forever. And there is a thought that follows naturally from this, the kind of thought that comes to you in the dark when you are half between waking and sleep, and the big things feel closer than usual. The two lobes of 67P were once separate. We know this now, with as much certainty as careful science allows. They were separate ancient bodies, formed independently in the cold outer reaches of the young solar system, each accumulating its own mass and layering its own ices in its own time. And at some point, over some long and gentle interval, they found each other, and they drifted together, and they fused, slowly and without violence. A meeting at a walking pace in the language of the dossier. Less an impact than a settling, but the crack in the neck suggests that what was joined may one day come apart. Not soon, perhaps, not in any lifetime we can imagine, but over future orbits, as the comet returns again and again to the warmth of the inner solar system and heats and outgasses and spins a little faster and stresses its narrowest point, that fracture could deepen and the head could separate from the body. And two things that had been one for billions of years would become two again, drifting apart in the dark, the same slow way they once drifted together. The duck may become two smaller ducks, or two plain rocks, or nothing more than a cloud of dust and ice slowly spreading through an orbit no longer shared. But that is a future the duck will meet without us watching. For now it remains whole, and the crack is just a crack, and the neck is still holding, and the whole small world still turns together, head and body and the narrow Hapy between them, carrying its ancient fracture as patiently as it carries everything else. Now let us speak about the turning itself, because that too is one of the duck's quiet facts. One of the things that makes it feel less like a distant rock and more like a living system, a place with its own rhythms and its own kind of time. 67P rotates once every 12.4 hours. A day on the comet, measured by one full rotation, is roughly 12.5 of our hours, shorter than a day on Earth, which turns once in 24. The comet is a slightly faster spinner than we are, and if you were standing somewhere on its surface, In one of those regions named for Egyptian gods, you would watch the sun rise and cross a black sky and set in just over 12 hours, and then you would wait another 12 hours in the dark, and it would rise again. Assuming, of course, that you could stand there at all, which the comet's gravity would make rather difficult to do for any length of time, for reasons we have already visited and will come back to again. But here is the detail about the rotation that I find particularly wonderful, in the way that only a very specific and slightly unexpected scientific fact can be wonderful at the right hour of the night. The comet's rotation did not stay constant while Rosetta was watching. It changed, and it changed because of the comet itself. As 67P warmed on its approach to the sun, it began to outgas more vigorously, releasing jets of frozen material that had been locked inside for billions of years. And those jets, streaming off the surface and into the vacuum of space, exerted a tiny, consistent force on the comet. The physics of this is the same as any jet. Push gas one way, and you push the source the other way, slightly. Individually, each jet is negligible, too small to matter against the momentum of a world 10 billion tons in mass. But over weeks and months of constant outgassing, the effect accumulates. It is the same principle as blowing on a pinwheel to make it spin faster. The comet blew on its own pinwheel, and it spun faster. Rosetta's observations showed that the comet's rotation period shortened by about 20 minutes during the period it was being studied. 20 minutes is not nothing. 20 minutes taken off a 12-and-a-half-hour day means the world is spinning measurably faster than it was. The comet changed its own rotation with the force of its own breath, which is, if you think about it slowly and let it settle, a rather extraordinary thing for a 4-billion-year-old frozen world to do. And now the surface. Because all of this, the shape and the rotation and the crack in the neck, is context for what the duck actually looks like up close, and up close it is stranger and more varied and more textured than any smooth and simple picture of a comet might have prepared you to expect. There is a boulder on the plane of the comet called Cheops, named, like the neck, for an ancient Egyptian reference, in this case the Great Pyramid of Giza, which the boulder was felt to resemble in its proportions. Cheops the boulder is roughly 45 meters wide and 25 meters tall, which means that if you placed it in a city, it would occupy roughly the footprint of a large building and rise as high as an 8-story one. It sits on the flatter terrain of the larger lobe, not embedded in the surface, but resting on it, casting its shadow across the surrounding rock and ice, one of the largest of many house-sized boulders scattered across the plains. Where it came from, Cheops specifically, is not entirely clear. There are boulders all over 67P, and they got there by various routes eroded from cliffs, flung up by outgassing events, and then settled back, or perhaps simply never moved from wherever they happened to be when the comet first took shape. Cheops is large enough to have remained where it is through considerable activity, a landmark on a landscape that has no permanent landmarks in any human sense. It has been there for a very long time, and Rosetta photographed it carefully, and now it has a name and a small measure of human recognition sitting out there in the dark on a rotating duck in the cold between Mars and Jupiter. Beyond Cheops and the other boulders, the surface of 67P has features that would seem more at home in a terrestrial landscape than on a comet in deep space. There are dunes, not dunes of sand, because there is no wind in the way we understand wind, no thick atmosphere pushing particles around. But there are ripple-like patterns on the surface that appear to function like dunes, shaped by the gentle flows of gas escaping from the comet's interior. As the gas streams across the surface on its way into space, it carries fine dust with it, and that dust settles and collects in wave patterns, soft ripples that look, in the images Rosetta returned, remarkably like the wind dunes of a desert, even though the mechanism producing them is entirely different. It is one of those moments where the universe turns out to have more imagination than we gave it credit for, finding ways to create familiar shapes through unfamiliar means, writing the same lines in completely different inks. And then there are the goosebumps. That is the informal name researchers gave to certain features on the comet's surface, particularly on some of the cliff walls, where the rock or ice presents not a smooth face, but a surface covered in small, rounded protrusions, each one roughly 2 to 3 meters across, clustered together in close, irregular groups. They look, in the images, like the surface of skin in cold air, hence the name. But the goosebumps of 67P are not a surface texture in the way that stone or ice might simply appear bumpy when you look closely. Scientists think they may be something far more significant than that. They may be the original building blocks of the comet itself. The ancient grains, called cometesimals, the pebble-sized clusters of ice and dust that first accumulated in the outer solar system, swept together by gentle gravitational attraction and by simple proximity, sticking and accumulating over millions of years into the larger lobes that eventually became 67P. If this interpretation is correct, and it is still a hypothesis rather than a certainty, then the goosebumps are not just surface texture. They are the comet showing you its own earliest layer, the raw material of its own assembly, preserved on exposed cliff faces for 4.5 billion years, waiting for a robot to fly close enough to photograph them. The idea that you could look at a 3-meter bump on a comet wall and see something that has not changed since before the planets formed is the kind of thought that benefits from a dark room and an unhurried mind. Let it sit with you for a moment. There is no rush. The surface also moves. Not quickly, not dramatically, but measurably. Rosetta watched 67P long enough and closely enough to document change, which is a remarkable thing in itself, a spacecraft patient enough to see a world shift over months. A boulder, tracked by Rosetta's cameras over the course of its mission, moved roughly 140 meters from its original position. 140 meters. Nudged and rolled by outgassing beneath it, by the subtle forces of a comet warming and contracting and venting in its slow approach to the sun, a house-sized rock shuffled across a plain in months in a way that would be invisible if you only had one photograph taken at the start and end, but became clear when you had enough images in between to track the change. Cliff faces crumbled, fresh material was exposed. The landscape of the duck was not static, not a fixed and frozen museum piece, but something alive in its own slow way, rearranging itself quietly over the months that Rosetta watched. And beneath the surface, just centimeters down, there is something unexpected. We know this because of Philae. We know this because even in its chaotic, bounced, tilted, shadow-bound landing, the little lander managed to measure things, and one of the things it measured was what the ground was actually made of. Philae carried an instrument called MUPUS, which stands for a long German acronym but can be thought of simply as a thermal probe and hammer. It was designed to be driven into the comet's surface to measure temperature and physical properties at depth. And when MUPUS tried to hammer its probe into the ground, it met resistance. Not the soft, compressible, loose surface that some models had predicted, not a deep snowdrift of fluffy ice, but something hard. Ice, as hard as solid rock, the data suggested. Dense, compacted, consolidated ice, just centimeters below the dark, dusty skin of the surface. Harder, in fact, than fresh snow or even ordinary ice from a freezer. More like the dense, blue-white glacier ice that forms under long years of compaction and pressure. The surface of the duck is covered in a layer of dark, dust-rich material, relatively loose and fine, almost like a thin coat of dark powder over the harder material beneath. But push through that layer even a short distance, and the comet becomes unexpectedly solid. Not rock, but ice so old and so compressed and so far from any warmth that it has lost most of its give, and it pushed back against Philae's hammer with a stubbornness that the probe was not fully designed to meet. This is part of why the comet is so dark. The surface is coated in carbon-rich organic compounds and dark, dusty residue, the remains of ice that sublimed away over billions of perihelions and left its darker, more complex chemistry behind. Beneath that coating, there is ice. And deeper still, presumably, there is the original ancient material, the pristine stuff that has never seen sunlight, that froze in the very first years of the solar system and has been kept cold ever since. The duck is, in that sense, layered, not in a metaphorical way, but in a structural and very literal one. And this brings us to another of its quiet wonders, one that requires Rosetta to have been patient and precise, and to have orbited closely enough to look at the cliff walls in detail. The cliff walls of 67P reveal terraces, stacked horizontal layers visible in cross-section where the comet's surface has eroded or collapsed to expose what lies beneath. Each layer, each terrace, is a record of a period of accumulation, a time when material settled onto this lobe and then was buried by the next layer above it, and so on, building up over time in orderly sheets. Scientists describe the layering as being like the pages of a book, layer upon layer upon layer, each one a chapter in the comet's accumulation, each one adding to the record of how this body built itself up over millions and billions of years. And because the two lobes each have their own independent layering, their own separate sets of pages that run inward toward each lobe's own center, rather than across both lobes together, the book metaphor becomes more precise. It is not one book. It is two books pressed together, spine to spine, each with its own pages, its own chapters, its own beginning. The contact binary made visible in the geometry of its own geology. The strata in each lobe converge toward a center point, like the rings of an onion, telling you where each lobe started and how it grew outward from there. And the two sets of strata, two sets of onion rings, two sets of layered pages, lie side by side in the neck, not aligned with each other, not continuous, but independent. The geological evidence for two separate origins, preserved in the rock and ice of the fused body, as though the comet has been holding its own birth certificate all this time, waiting for someone to fly close enough to read it. There are also pits, deep, round, steep-walled pits that open on the surface like wells or skylights, some of them tens of meters wide and just as deep, their floors dark and their walls bright with exposed ice. Scientists have studied these pits carefully, and the most widely supported explanation for how they form is a process of subsurface collapse. A hollow pocket forms just beneath the surface, perhaps where volatile material has sublimed away and left an empty space. And eventually the ceiling of that hollow becomes too thin to support itself and caves in, opening a pit to the sky above. Sinkholes, not so different in their basic mechanism from the sinkholes that open without warning in limestone country, in Florida or in the Yucatan, or in any place where water has slowly eaten out the rock below the surface and left a void. On 67P, the process is ice subliming instead of rock dissolving, vacuum instead of water, and the time scale is different, but the fundamental geometry of it, a roof collapsing over a hidden void, is something the Earth knows too. And some of these pits are not quiet. Some of them are active, venting gas and dust from their floors. The freshest material on the comet, exposed to sunlight for the first time, subliming vigorously and sending jets of gas and fine particles streaming upward from the pit's shadowed depths. The most active pits on 67P are like tiny volcanoes, not of molten rock, but of escaping ice, their walls bright and their floors busy, windows into the comet's interior that the comet itself has opened. You could sit in one of those pits, if you were small enough and patient enough and dressed for the cold and the hard vacuum, and watch the walls around you slowly retreat, the ice subliming grain by grain in the sun. Fresh material appearing behind it, ancient material that has never before seen sunlight becoming sunlight's newest subject. You would be sitting inside the comet's interior, in a room the comet made for itself, watching the walls slowly dissolve. It would take a very long time. But you would have the time, in that place, and no particular reason to be elsewhere. Of course, there is no one in those pits. There is no one on the comet at all, and has never been. There is only the surface turning slowly in the cold, the long days and the long nights. The dark dust layer and the hard ice beneath it, and the strata below that. The goosebumps on the cliff walls and the boulder Cheops standing alone on the plain. The crack running through the Hapy neck like a sentence that has not yet reached its period, the dunes shaped by escaping gas, and the pits opening like quiet questions into the comet's ancient interior. It is a small world, 4 kilometers end to end. You could walk from one side to the other in an hour, if the gravity allowed you to walk, and if the terrain were flat, which it is not. Instead, you would drift across it, half walking and half floating, one careful step at a time, aware that a slightly misjudged push might lift you off the surface entirely and send you drifting upward into the coma and eventually into space. The duck holds you very loosely. It does not insist on your presence. It simply offers what it has, the surface beneath your feet, the dark sky above. The stars visible through the tenuous veil of gas and dust that surrounds it, and the strange quiet of a place where nothing has ever happened quickly. The comet has been here for 4.5 billion years, and in all that time almost nothing about it has changed, deep down. The layers were laid, the two lobes fused, the crack began to form, the dark dust accumulated on the surface. And the whole thing went on rotating and orbiting, warming and cooling with each pass of the sun, losing a little of its ice each time, carrying its ancient chemistry unchanged in its heart. Patient in the way that only a thing with no ability to be impatient can be. Serene in the way that only emptiness and cold can produce. And then, in the relatively recent past, in the fraction of a cosmic second that is the history of our species, a few hundred people in buildings on a small planet looked at a photograph taken at an observatory in Kazakhstan and noticed a smudge near the edge of the plate that did not belong to the comet they had been trying to photograph. And the smudge was given 2 names, and the numbers were run, and the orbit was calculated, and the shape began slowly to be known. And then, much more recently still, a spacecraft was built and launched and aimed outward, beginning the long and winding chase that would eventually bring Rosetta to this duck-shaped world, to spend 2 years flying close and watching and measuring and listening, while a small lander drifted down through the faint gravity and reached the surface and bounced, and reached it again and rested in the dark. But that part of the story, the spacecraft and the journey and the landing and all the things that were found, is the part that waits for you just ahead. Deeper in the night, when you are deeper still in your rest. For now we have looked closely at the duck itself. We have measured its body and its head and the neck between them. We have walked along the crack in Hapy and felt the slow tension of 2 ancient things that may be slowly parting. We have looked at the goosebumps on the cliff walls and understood what they might mean. We have watched the boulder shuffle 140 meters across the plain and pressed our hand against the hard ice just beneath the dark surface, and sat at the edge of a collapsing pit and watched the fresh interior of the comet emerge, blinking into the cold light of a sun that is very far away. The duck is a real place. It has real terrain. It has a day that is 12.5 hours long, a rotation that's shortened by 20 minutes from the force of its own breath, a surface that moves and changes and vents and collapses and surprises you when you look closely. It is not a simple rock. It is not a simple anything. And now let your mind rest on the surface for a moment, if it wishes to. Settle somewhere on the plain near Cheops, in the shadow the boulder casts in the low, faint light. The surface beneath you is dark and very fine, like the ash at the edge of a very old fire, and it gives slightly underfoot, but not much. A few centimeters down is the hard ice, and below that the layers begin. Page after page of time, written in ice and dust and dark carbon. The horizon is very close. Because the comet is so small, the curve of the world visible just a few kilometers away in every direction. The sky above is black and full of stars, and the coma, the thin veil of gas and dust the comet breathes out as it warms, catches the distant sunlight and gives the sky a faint luminescence. Not quite a glow, but almost a softening of the black. It is quiet. Whatever sound means in a vacuum, there is none of it here. The comet makes a sound, but not in any medium that ears were made for. Not vibration through air, but an oscillation in the magnetic field around it. Something that requires instruments to hear and mathematics to convert into anything audible. We will get to that sound in a little while. It is one of the facts still waiting for you further down the night, a strange and gentle fact about what the comet hums to itself as it moves. For now there is just the plain, and the boulder, and the stars, and the slow rotation bringing the distant sun around again, and the crack running through the neck somewhere just out of sight, working itself open grain by grain across the passage of years. The duck turns, the dust settles, the hard old ice holds in the cold, and there is more to tell. 31 years before Rosetta reached the comet, engineers and scientists in Europe began talking about what it might mean to chase one. Not to fly past, not to observe from a respectful distance, not to infer its chemistry from the light it scattered across a telescope lens in some quiet observatory, but to actually go there, to follow a comet through space for years, to slow down until you were moving with it at the same pace, in the same direction, like a companion animal that has learned to match its step to yours, to orbit it, to set something down on it, The idea was audacious in the way that ideas are when they are first proposed, before the audacity has been absorbed into planning documents and budget cycles and the long, practical business of building things that must not fail. The mission that eventually became Rosetta was formally approved by the European Space Agency in 1993. That is a date worth holding for a moment. 1993. The spacecraft would not launch for another 11 years. It would not reach the comet for another 21 years. And the people who approved it in 1993 knew this and approved it anyway, which is its own quiet kind of faith. 33rd fact about the comet and the mission that went to find it. Rosetta launched on 2nd March 2004. It left the ground from the Guiana Space Center in Kourou, French Guiana, carried by an Ariane 5 rocket, and within minutes it was past the atmosphere and past the weather and past everything that word means on the surface of the Earth. The year was 2004. The comet, at that moment, was somewhere out past the asteroid belt, drifting on its long, slow arc toward the outer solar system. Rosetta and 67P were in the same solar system, but in no particular relationship to each other yet. That relationship would take 10 years to build. 29th fact. The winding route from Kourou to the comet stretched approximately 6 billion kilometers, 6.4 billion more precisely, which is a number that resists direct comprehension but can be approached through smaller numbers. The distance from the Earth to the Sun is about 150 million kilometers. Rosetta travelled more than 40 times that distance, not in a straight line, but in great curving arcs, looping back and forward and around the inner solar system in the patient, circling manner of something building up to a leap. A direct shot to the comet was not possible. The orbital mechanics would not allow it. You cannot simply point a spacecraft at a comet and fire. You must calculate where the comet will be years hence and send the spacecraft there instead, and to do that you must first build up enough speed, and to build up enough speed without carrying the fuel to do so, you must borrow momentum from the planets themselves. 30th fact. Rosetta borrowed that momentum 4 times. It flew past Earth 3 times and past Mars once, each time approaching at an angle that let the planet's gravity catch it and spin it a little faster, a little further around its long arc before releasing it with more energy than it had arrived with. Think of it the way you might think of a ball on a string being swung in a wide circle. Each pass through the lowest point carrying a little extra speed. The planets are not actually depleted by this. The spacecraft takes momentum from a body so immensely massive that the effect on it is unmeasurable. But the spacecraft changes course. It accelerates. It is free. 31st fact. The Mars flyby in 2007 was the most precise and the most alarming of these gravity assists. Rosetta skimmed within 250 kilometers of the Martian surface, close enough that it briefly passed into the planet's shadow, the Sun hidden behind Mars, the spacecraft running entirely on its batteries for an agonizing stretch of minutes. Mission controllers at the European Space Operations Centre in Darmstadt had taken to calling that particular manoeuvre the billion-euro gamble, which is not a phrase that suggests easy confidence. The entire investment in the mission, the years of engineering and the careers of thousands of people and the scientific questions that had waited decades for answers, all of it hung on a flyby that ran through a planetary shadow on stored battery power and could not be corrected if something went wrong. Nothing went wrong. Rosetta emerged from the shadow of Mars and found the Sun again, and its solar panels began to drink light, and the spacecraft continued on its long, curving road toward a comet it would not reach for 7 more years. 32nd fact. On the way, it stopped twice, or rather it did not stop. Nothing in space truly stops, but it passed close enough to 2 asteroids to see them clearly, to photograph them and measure them and learn something about what the early solar system left behind. The first was asteroid 2867 Teens, which Rosetta flew past in September 2008. Teens is small and bright and oddly diamond-shaped, a rocky body knocked and scarred by billions of years of collision, its surface cratered in the patient, permanent way that airless worlds accumulate damage. Then, in July 2010, Rosetta swept past 21 Lutetia, a far larger body, irregular and ancient-looking, its face pocked with enormous craters and covered in the grey rubble of its own long history. These were not primary mission targets. They were gifts from the trajectory, windows in the route where Rosetta happened to pass close enough to take a portrait, and the scientists were glad of them. Then the comet was still too far, and the sun was too faint, and the mission entered a kind of suspended state. 33rd fact. In June 2011, Rosetta was put to sleep. Not metaphorically, the spacecraft was placed in deep space hibernation, most of its systems switched off, all the instruments powered down, the communication systems silenced. For 31 months it drifted in the cold and dark, in the outermost reach of its orbit, saying nothing to anyone, receiving no commands, carrying out no measurements. 31 months is nearly 2.5 years. The people who built Rosetta and flew Rosetta and had spent years thinking about the comet Rosetta was going to find, those people went about their lives and did other things and waited. The spacecraft drifted. And then, on 20 January 2014, an alarm clock inside Rosetta that had been set years before and never changed finally reached its moment and went off. Systems began to wake. The spacecraft warmed. The transmitter came back to life. And a signal crossed the darkness and reached the dishes of the Deep Space Network and was received at the European Space Operations Centre in Darmstadt, Germany. The mission team, who had been waiting in the control room through a long and tense morning, saw the signal arrive and understood what it meant. Someone posted a message to the spacecraft's public account that said, "Hello World, 34th fact." That was the message. Hello World, simple and deliberate and exactly right. The spacecraft had been asleep for nearly 3 years. It had woken itself up by its own alarm in the cold and dark of deep space with no help from anyone, and it had said hello. The people in that room had been waiting for years for that moment, and it came on a Tuesday in January 2014, and there was a great deal of noise in the control room, the kind of noise that only comes out when something that has been held very tightly is finally allowed to release. Rosetta was awake. The comet was ahead. There were still months of approach and calibration before the arrival, but the long silence was over. 35th fact. The power that kept Rosetta alive through all of this, the 10-year journey, the hibernation, the wake-up, came from sunlight. Rosetta carried no nuclear power source. It ran entirely on 2 great solar wings, each panel spanning the length of many people standing end to end, together stretching 32 meters from tip to tip across the darkness. This was, at the time, not a given. The received wisdom of deep space mission design was that solar power became impractical beyond a certain distance from the sun, because the sunlight gets too thin, too diluted by the vast volume of space it must fill as it travels outward. Rosetta was designed to challenge that assumption, to prove that with large enough panels and careful enough power management, a spacecraft could live on sunlight even as far out as the asteroid belt and beyond. It proved this. Rosetta operated under solar power nearly 800 million kilometers from the Sun, a record for solar-powered spacecraft at the time, and it operated quietly, and it did not fail. 36th fact. Rosetta arrived at Comet 67P/Churyumov-Gerasimenko on 6 August 2014. That sentence has 12 words in it, and they do not convey the weight of what happened on that date. A machine that had been built on the ground in Europe, launched in 2004, swung around the inner solar system on borrowed planetary momentum for 10 years, slept for 31 months in the cold, woken itself with an alarm, and then spent months carefully braking and maneuvering, arrived at a comet 4 kilometers wide in the outer solar system on 6 August 2014 and became the first spacecraft in history to orbit a comet. No one had done this before. No machine had ever escorted a comet around the Sun. And then Rosetta did it, and began to circle 67P in careful arcs, sometimes only a few kilometers above the surface, close enough to resolve individual boulders in its cameras, a tiny metal satellite around a tiny dark world. Now, before following Rosetta and the comet further into 2014 and the months that followed, it is worth pausing on the names, because the names are not incidental to the story. They were chosen with particular care, and they carry the weight of what the mission was trying to do. 38th fact. The spacecraft is called Rosetta after the Rosetta Stone. The Rosetta Stone is a granodiorite slab discovered in Egypt in 1799, which carries the same decree written in 3 scripts: ancient Egyptian hieroglyphs, Demotic script, and ancient Greek. Because scholars could read ancient Greek, the stone became the key that unlocked a writing system that had been unreadable for more than 1,000 years. It turned an undecipherable symbol set into language, and the Rosetta mission, named after it, was conceived as an attempt to do something analogous, to read the frozen record of the early solar system, to decode what the comet had been preserving for 4.5 billion years, to use a dead stone as a key to very old writing. The name is not decorative, it is precise. 39th fact. The lander is called Philae. Philae is an island in the Nile, or rather it was. Most of it now lies beneath the waters of Lake Nasser, submerged after the Aswan High Dam was built. But from the island of Philae came an obelisk, the Philae obelisk, which carried bilingual inscriptions in Greek and Egyptian hieroglyphs, and which was studied by the Egyptologist Thomas Young in the early 19th century and contributed to the eventual decipherment of hieroglyphs. The lander and the orbiter share a single linked purpose expressed through 2 objects from the same historical act of unlocking. The stone and the obelisk, the orbiter and the lander, both involved in the same reading of very old text. 40th fact. Rosetta carried something else besides its instruments and its fuel and its careful mechanisms. Bolted to the spacecraft was a small disk made of nickel, etched with text so small it required a microscope to read, holding samples of more than 1,000 human languages. The project was called the Rosetta Project, run by the Long Now Foundation, which had the idea that a comet moving through space for millions of years was an appropriate place to archive human languages against the possibility that some of them might be lost. It is perhaps the strangest cargo Rosetta carried: not science, not fuel, not navigation hardware, but a library, a tiny library of voices sent out to ride a comet in the dark, held together with instruments that would measure molecular oxygen and the ratio of heavy hydrogen to light hydrogen. Somewhere on 67P now, that disk is still attached to Rosetta's body, resting where the spacecraft came to rest, and all the languages it carries are still there, still legible in principle to anyone with a microscope and sufficient time. But Rosetta arrived first with Philae still attached, and there was a landing to attempt. 41st fact. Philae was the first machine ever to land softly on a comet. That is the single most compressed way to say it, and it does not capture very much of what the landing was actually like. Let us try to say it more fully. The landing happened on 12 November 2014. Philae was a box roughly the size of a washing machine, three-legged, built with instruments for drilling and hammering and sniffing and measuring, designed to touch a surface that no one had ever touched, and to survive there long enough to do science. It had been travelling through space attached to Rosetta for the 10 years of the journey, patient and cold, waiting for its single moment of purpose. 42nd fact. The descent from Rosetta to the surface took approximately 7 hours. 7 hours of falling in a nearly featureless drop toward a dark world whose gravity was so weak that the word falling becomes somewhat misleading. In any ordinary gravity, falling is a committed, accelerating act. On 67P, in an environment where the gravitational pull is roughly 100,000 times weaker than Earth's, falling is more like very slow drifting, an uncommitted descent that could almost be reversed by a firm breath. Philae drifted downward over the course of a long morning from the controller's perspective across roughly 20 kilometers of space, unhurried, turning gently in the barely there gravity field, while the people who had built it and the people who had flown Rosetta to find it watched the numbers come back from across the solar system on a signal that itself took 28 minutes to travel the distance. And then Philae reached the surface. 43rd fact. It was supposed to be anchored. Philae carried harpoons, 2 of them, 1 in each leg, designed to fire into the ground on contact and pin the lander down against the surface, holding it against the gentle but persistent pull to float back up. In an environment with so little gravity, anything that bounced on landing would keep bouncing for a very long time before the comet's weak pull drew it back, if the comet's pull drew it back at all. The harpoons were the answer to that problem. They would fire, they would penetrate, they would hold. That was the plan. The harpoons did not fire. 44th fact. A cold gas thruster on the top of Philae, designed to push down on the lander at the moment of touchdown, pressing it into the surface at exactly the instant the harpoons were firing, so that the whole mechanism worked together, had failed in the days before the landing. Engineers knew about this failure and knew they could not fix it. They sent Philae down anyway, and the thruster did not push, and the harpoons did not fire, and the surface came up, and Philae made contact, and had nothing to hold it, and so it bounced. 45th fact. It bounced. This is the word the mission used, and it is the right word, and it is also slightly absurd, in the particular way that scientific events sometimes are when they occur on bodies with no ordinary relationship to the physics of daily life. Philae hit the surface of Comet 67P/Churyumov-Gerasimenko on 12 November 2014, and with no anchor and no thrust and the gravity of a feather holding it down, it rebounded. Back up, back into space. Off the comet it had travelled 10 years and 6 billion kilometres to find. 46th fact. The first bounce lifted Philae nearly a kilometer above the surface. It sailed upward and continued to drift for nearly 2 hours, turning slowly in the dark. Before the comet's barely there, gravity drew it back down again. A kilometer high. 2 hours of unanchored flight. The lander drifted in the thin coma of gas and dust the comet breathes out. With the distant sun somewhere above and the dark surface somewhere below, and the people in Darmstadt watched the telemetry and understood what was happening, and there was very little they could do. 47th fact. Philae came down again and bounced a second time. A shorter hop this time, a few minutes, a smaller rebound from a lower height, the energy of the initial landing slowly dissipating as the lander continued to tumble and settle across the surface in its strange, slow ricochets. And then it stopped. 48th fact. Philae came to rest in a region of the comet called Abydos. Abydos is named, like all the regions of 67P, for an Egyptian place or deity, continuing the chain of Egyptian names that extends from the Rosetta Stone through the lander's name and across the entire surface of the comet. Every crag and cliff and flat and pit carrying a name from the same ancient civilization whose scripts the mission was metaphorically trying to read. Abydos in Egypt is the site of temples and royal tombs, a place of deep antiquity and ritual significance, a place where things were meant to be preserved and remembered. On 67P, the region called Abydos turned out to be a shadowed crack or crevice or cliff face. The exact geometry took nearly 2 years to establish, and Philae was wedged somewhere inside it, tilted at an angle. One leg lifted into the dark, the other two resting on some surface that the cameras aboard could partially see and partially describe, but could not fully map. 49th fact. The shadow was the problem. The landing site that had been chosen for Philae before the mission, the flat, sunlit plain with reasonable clearance and good solar angles, was not where the lander ended up. The 3 bounces had carried it somewhere else, and somewhere else, in the region of Abydos, happened to receive only a few hours of weak sunlight per comet day. A comet day is 12.5 hours long, and Philae's solar panels needed more light than the crack in Abydos would give them. The comet was still far from the sun in November 2014. The light was thin to begin with, and the shadow made it thinner still. Philae's panels drank what light they could, and it was not enough. 50th fact. What happened next is one of the more quietly extraordinary things in the history of space exploration. Philae, running on its primary battery rather than on solar power it could not collect, spent approximately 60 hours doing science. 60 hours of measurements and drillings and chemical sniffings and hammer blows into the ice below, the lander working through its battery reserve with a kind of systematic completeness that suggested the people who had programmed it understood at some level that the battery might be all they got. The instruments ran. The data came back. Philae returned the first measurements ever taken directly on the surface of a comet, tilted in a shadow on a small dark world 4 kilometers wide, 2.5 hours of signal travel from anyone who could help it. And then the battery drained, and Philae went quiet. The silence began on 15 November 2014, roughly 60 hours after touchdown. The lander went to sleep in its shadowed crack, and the comet continued its orbit, and Rosetta continued to circle above, and the months went by. 51st fact. 7 months later, in June 2015, as the comet moved closer to the sun on its long inward arc, and the sunlight reaching Abydos grew stronger and began to penetrate the shadow a little more, Philae woke up. Briefly, it woke, and it sent a signal to Rosetta, and Rosetta received it and relayed it back to Darmstadt, and for a few short bursts across a period of days, the lander was alive again and communicating, sending bits of data and status reports from its dark crevice. The first contact lasted 85 seconds. Others followed, scattered and intermittent, the signals sometimes incomplete, the connection uncertain. Engineers tried to send commands, to understand the lander's orientation, to plan for more science, but the contact was never stable enough to accomplish very much, and after a handful of brief awakenings, Philae went quiet again and did not wake a third time. 50-second fact. No one knew exactly where Philae was for nearly 2 years after the landing. The instruments had given partial information about the environment around the lander. The cameras had captured partial images of rock surfaces and shadow, but the precise location, which crack, which cliff, which particular patch of the comet's fractured face, remained unknown. The comet's surface is large enough and varied enough and dark enough that identifying a washing machine-sized object wedged into a shadowed crevice was not a simple task from orbit, and Rosetta's closest passes in the early months of the mission had not been close enough to find it. Then, on 2 September 2016, just a few weeks before the mission was to end, Rosetta's OSIRIS camera finally spotted Philae. The image showed it there in the rock face, propped at its tipped angle, its body partly in shadow, one leg extended upward into the thin coma, its solar panels catching a little of the distant light, but not enough, not anymore. The shape was unmistakable once you knew what you were looking at. There was Philae where it had rested for nearly 2 years, in a fracture on the surface of a comet in the outer solar system. The mission controllers, who would end the Rosetta mission just 4 weeks later, now knew where both their spacecraft were. Rosetta orbiting above, Philae resting in Abydos below. 53rd fact. Even in the shadow, even tilted and cold and unable to fully power itself, Philae had done what it was meant to do. The 60 hours of battery-powered science it completed in November 2014 returned the first in situ measurements ever taken on a comet's surface. The hammer that drove into ice as hard as rock, the instruments that sniffed the chemistry around it, the measurements that contributed to what Rosetta would later find orbiting above, the oxygen, the glycine, the noble gases, the wrong water. Philae's data was part of the picture, the part taken from the inside, from the surface itself, rather than from instruments hovering a few kilometers above. A machine that bounced a kilometer off a comet and ended up tilted in a shadow with a partially dead battery still returned information that humans had never had before. And Rosetta continued to orbit. And the comet continued to warm as it moved toward the sun. And there were still things to discover, things that would require Rosetta's instruments circling above for months more, watching the comet wake up and breathe and sing. Because the comet was singing. That fact was waiting, as was mentioned earlier, and the time has nearly come to explain it properly. But first consider for a moment the whole length of the chase, laid out as it actually was. 11 years of planning before the launch, 10 years of flight to reach the target, 31 months of hibernation in the cold, a self-woken alarm on a Tuesday in January, months of approach, the first orbiting of a comet in human history, a 7-hour drift down to a surface, 3 slow bounces, a shadowed crevice, 60 hours of battery science, a brief whisper back in June, and then 2 years of not quite knowing where the lander was until the camera found it in a crack. All of this happened, not as a story someone shaped for meaning, but as a sequence of engineering decisions and orbital mechanics and battery readings and signal delays and a cold gas thruster that failed and harpoons that did not fire and a machine that woke itself up in the dark of the outer solar system and said, "Hello, world." The comet was there for all of it. Turning in its 12-and-a-half-hour days, its neck slowly cracking, its surface dark as charcoal, its layers holding their 4.5 billion-year record of what the early solar system was made of. The comet did not know about any of this, of course. It cannot know. It is ice and dust and dark organic carbon and a growing fracture through the narrowest part of its neck. Circling the Sun on the same 6.5-year arc it has followed for longer than the Earth has had oceans. But Rosetta was there. Rosetta was there for years, circling a few kilometers above the surface in its careful navigated arcs, its instruments drinking in everything the comet could tell about itself, and the comet had a great deal to tell. The solar panels stretched their 32 meters and drank the thin, distant sunlight. The cameras resolved boulders and dunes and goosebumps and a crack over 500 meters long and growing. The spectrometers sorted the gases streaming off the surface as the comet warmed. The magnetometers felt something in the space around the comet. Something oscillating at a frequency far below the lowest note a human ear can register, a physical variation in the magnetic field that the instruments recorded and that scientists, when they had time to look at the data, would convert into sound. The comet was making something that, with the right translation, could be called a song. And all of that is still ahead, further along the night. The oxygen that was not supposed to be there, the amino acid found in the thin gas around the comet, the heavy water that was not like Earth's water at all, and what that means for the old question of where the oceans came from. The aurora no one had expected to find wrapping the comet in faint ultraviolet light. The perihelion, the closest point to the Sun, on 13 August 2015, when the comet was at its most active, and Rosetta watched from a careful distance as jets of gas and dust burst from the surface with a force and frequency that made navigation difficult. The deliberate, walking speed descent that ended the mission. All of that is still ahead. The comet is still circling the Sun, right now on its 6.5-year arc, and Rosetta is still there on its surface, resting near a pit named Deir el-Medina in the region called Ma'at, and the disk of more than 1,000 human languages is still attached to its body, still legible in principle, still carrying all those voices through the dark. The comet hums its inaudible hum. The crack in the neck works itself open, grain by grain, across the passage of years. The surface rotates through its 12-and-a-half-hour day, each sunrise triggering small bursts of gas from the frozen patches that the night has let grow cold again. Somewhere in the region of Abydos, tilted in its shadowed crack, Philae rests with one leg in the air. And there is still more to tell. Fact 54. The comet sings. That sentence needs a moment to settle because it is stranger and more real than it first appears. It is not a metaphor. It is not a poet's shorthand for something else. When Rosetta approached 67P in the late summer of 2014, still weeks from orbit, its RPC magnetometer, the instrument designed by a team led by Karl-Heinz Glasmayer, built to measure the faint electric and magnetic fields threading the space around the comet, began detecting something unexpected. A low oscillation, a repeating ripple in the magnetic field, steady and strange, produced by the way the comet's thin envelope of outgassing interacted with the solar wind, the constant stream of charged particles flowing outward from the Sun. The field around the comet was not still. It was pulsing, but pulsing at about 40 to 50 millihertz, which is a frequency so far below the threshold of human hearing, roughly 40,000 times lower than the lowest note a human ear can register, that no person alive could ever hear it directly. The lowest note on a piano sits at about 27 hertz. The lowest rumble most people can feel, more than hear, is around 20 hertz. The comet's song runs at 40 to 50 thousandths of a hertz. It is not in our range. It has never been in our range. It has been singing, in all likelihood, for most of the solar system's history, and nothing with ears has ever been close enough or tuned correctly enough to notice. Scientists sped the recording up 10,000 times. When they did, what came out was an eerie, clicking, almost warbling sound, something between a distant woodpecker and the faint tick of a machine in a quiet room, low and irregular, with a quality that is hard to describe without reaching for words that are more poetic than scientific. People who heard the sped-up version described it as unsettling. Beautiful, some said, like something alive. And nobody had expected it. The discovery landed as a genuine surprise, announced in a short paper and accompanied by the audio clip, and for a brief, bright moment it drew the attention of people who had never thought about a comet before. The clicking warble spread across the internet. Some people called it a message. Some reached for the idea that the comet was something other than a comet, that the song was intended, that something had put it there. It was not. The exact cause is still being studied, still being untangled from the complex physics of how a tenuous gas envelope couples with a magnetized solar wind at this particular distance and this particular level of activity. But it is a natural phenomenon arising from the same processes that make the space around planets and moons hum and buzz with electromagnetic activity, scaled down to the size of a 4-kilometer duck drifting through the outer solar system. What makes it extraordinary is not the explanation, but the fact. This thing, this ancient lump of ice and carbon and frozen gas, travelling its slow 6.5-year arc in relative silence, is doing something that can be translated, with the right tools, into sound. The universe is not quiet. It is singing at frequencies we were never built to hear, and we had to send a robot to a comet 10 years away to find out. Fact 55, the song runs at about 40 to 50 millihertz, thousands of times below hearing. Scientists sped it up 10,000 times to make it audible. Fact 56, no one expected it. It was detected as Rosetta approached, and its exact mechanism is still being studied. Let those sit. And now the oxygen. Fact 57. The comet breathes out molecular oxygen, and that fact, when Rosetta's Rosina instrument first detected it in the gas streaming from 67P, produced something close to disbelief in the science team. Not because oxygen is rare in the universe, it is the third most abundant element, but because molecular oxygen, two oxygen atoms bonded together, is extraordinarily reactive. It bonds to almost everything it encounters. In the presence of carbon, hydrogen, silicates, organic molecules, all the materials a comet is made of, molecular oxygen should not last long. It should find something to attach to and become something else. The conventional assumption before Rosetta was that any O present at the formation of a comet 4.5 billion years ago would long since have reacted away, bonded itself into water or carbon dioxide or some complex organic compound, and ceased to exist as free molecular oxygen. But there it was, streaming steadily from 67p, measured by Rosina across hundreds of separate observations, absolutely consistent. Bieler and colleagues published the result in Nature in 2015, and it stood up to every scrutiny. The molecular oxygen was there, and it was there in quantity. Fact 58, that oxygen makes up about 3.8% of the water vapor coming off the comet. Nearly 4%. Steady and evidently primordial, frozen in since the solar system was new, somehow preserved through 4.5 billion years of cold storage, somehow surviving the occasional warming passages near the sun without fully reacting away. How? The working hypothesis is that the O formed in the cold molecular cloud that preceded the solar system before the sun even ignited, and that it was incorporated into the forming comet at such low temperatures that it became trapped in the ice matrix in a kind of frozen cage, a structure called a clathrate, which is like a molecular prison of water ice bars, and that this cage held it stable across geological timescales. The cold of deep space, billions of years out past Jupiter, kept the bars from melting. Each perihelion passage warmed the surface enough to release some, but the bulk stayed locked. It is the cometary equivalent of opening an old tin and finding the smell still there. And if molecular oxygen can survive 4 billion years frozen into a comet, then the question of what else might have survived opens up in a very specific direction. Fact 59. The comet carries glycine. Glycine is the simplest amino acid. Amino acids are the molecular units from which proteins are built, and proteins are the machinery of life, the enzymes, the structural components, the signaling molecules, the workers, and the scaffolding of every living cell. There are 20 amino acids in common biological use, and glycine is the smallest, the most chemically basic. The first one chemistry tends to make when the right ingredients are mixed together. Its molecular formula is CNO, 2 carbons, 5 hydrogens, 1 nitrogen, 2 oxygens. A small, simple thing. Rosetta's Rosina instrument detected it in the thin gas surrounding 67p. Catherine Altweg and her colleagues published the finding in Science Advances in 2016. It was not the first time glycine had been found in space. It had been detected in meteorites and tentatively in the gas around a star-forming region. But it was the first direct, in-place detection of an amino acid in the gas of an active comet. Not inside a rock that had fallen to Earth, not in a distant nebula, but right there, streaming off a known comet while a spacecraft watched. And alongside the glycine, phosphorus. Fact 60. The same measurements found phosphorus in the coma of 67p. Phosphorus is essential to life in ways that go beyond mere amino acids. It is the backbone of Dina and Rana, the molecules that store and transmit genetic information. Every strand of Dina in every cell of every living thing is linked together by phosphate groups, by phosphorus. It is also central to adenosine triphosphate, ATP, the molecule that powers almost all biological energy transfer. Without phosphorus, the chemistry of life as we understand it cannot run. Finding it streaming from a comet alongside a building block amino acid in the company of water and carbon dioxide and a zoo of organic compounds is not proof that comets seeded life on Earth. The science does not reach that far, and it is important to be precise about what it says and what it does not. But it is evidence, real, direct, measured evidence, that comets carry the raw materials, that the ingredients were out there, floating through the early solar system, available for delivery, that the distance between chemistry and biology may be shorter, and the supply chain longer and older than anyone had thought. Each orbit 67p makes, it loses a little of itself to the Sun. Some of that lost material, dust and ice and gas and organic molecules, eventually settles somewhere. 4.5 billion years ago, the solar system was full of comets, thousands of times more than today, and the young Earth was being struck by them regularly. The glycine and phosphorus detected at 67p are a window into what those ancient bombardments may have carried. Fact 61. The comet's water is not like Earth's water. This is the one that reshapes a theory. Water, Ho, is simple enough in formula, but in nature it comes in slightly different versions depending on the isotopes of hydrogen involved. Ordinary hydrogen has one proton and no neutrons. Heavy hydrogen, called deuterium, has one proton and one neutron. Both bond with oxygen to make water, but the heavy version, Sto, sometimes written as semi-heavy water, is slightly denser, slightly heavier, and its ratio to ordinary water varies depending on where and how cold the water formed. The ratio of deuterium to ordinary hydrogen, the DH ratio, is a kind of fingerprint. Different regions of the early solar system produced water with different DH ratios, and the ratio has been preserved in comets and asteroids ever since. By measuring the DH ratio in a comet's water and comparing it to the DH ratio of Earth's oceans, scientists hoped to determine whether comets like 67p were responsible for delivering the water that filled those oceans. Altweg and colleagues measured 67p's water using Rosina and published in Science in 2015. The DH ratio in 67p's water is about 3 times higher than Earth's oceans. 3 times. Not a small discrepancy, not a rounding error. A factor of 3. The water steaming off this comet is significantly enriched in heavy hydrogen compared to the water on Earth. They are not the same water. Whatever filled Earth's oceans did not come primarily from comets like 67p. Fact 62. That single measurement reshaped a long-standing theory about Earth's water. It does not mean comets contributed nothing. Some water may still have come from comets with a closer DH match, and asteroids remain strong candidates. But it means that this kind of comet, this Jupiter family comet from the outer solar system, is not the main source. The ocean origin question, which seemed close to an answer when Rosetta launched, turned out to be more complicated than expected. The wrong water pointed in a new direction. This is how science actually works. A mission designed partly to confirm a hypothesis found evidence that complicated it. That is a far more valuable outcome than simple confirmation. Fact 63. The comet holds ancient noble gases. Trapped in its ice, frozen in since its formation, Rosetta detected argon, krypton, and xenon, 3 of the inert gases, the elements that do not react with anything, that simply exist in their atomic form and carry their conditions of origin like a sealed letter. Rubin and colleagues published this result in Science in 2018. Noble gases preserve a chemical record of the temperature and pressure at which they were incorporated into the ice. Their presence and their ratios in 67p's material confirm that it formed in extremely cold conditions, far from the young sun, in a region of the early solar system where temperatures were so low that even noble gases could freeze into the forming comet. They have been sitting there ever since. Argon, krypton, and xenon locked in a comet that has circled the sun thousands of times, each orbit warming slightly, each perihelion releasing a thin breath, and yet still there, still measurable, still carrying their 4.5 billion-year-old message about where and in what cold they were born. And as all of this was being measured, as Rosina was tasting the comet's breath and finding oxygen and glycine and noble gases and wrong water, the comet itself was drawing closer to the sun. The relationship between 67P and sunlight is not constant. It is a slow, seasonal thing, governed by the comet's elliptical orbit and the tilt of its spin axis. And as Rosetta's mission progressed through 2014 and into 2015, the comet was moving inward. Fact 67, Rosetta watched the comet wake up as it neared the sun. This is something no spacecraft had ever done before, escorted a comet through its transformation, watched it change from a cold and relatively quiet object in the outer solar system into an active, outgassing, jetting thing. In the early months after arrival, 67P was already displaying some activity, small jets from the Hapy neck region, wisps of gas from the warmer patches. But as the orbit tightened and the sun grew from a distant lamp to something more pressing, the change was dramatic. Pits on the surface, the sinkholes where hollow subsurface pockets had collapsed, began to vent gas from their floors. The active pits glowed, with jets streaming upward from their shadowed depths, the freshest ice reaching sunlight for perhaps the first time in millions of years. The surface temperature, measured by Rosetta's Vertis spectrometer, climbed in the sunlit patches. Ice that had been stable in the cold was now sublimating, turning directly from solid to vapor without passing through a liquid phase. Because in the near vacuum of space, there is no pressure to sustain a liquid. The comet was evaporating. Fact 68. The comet has seasons and a brutal short summer. The tilt of 67P's rotation axis means the northern and southern hemispheres experience the sun very differently. The northern hemisphere has a long, gentle season. It faces the sun for most of the orbit, but at an angle that never gets too intense. The southern hemisphere has a short, furious summer at perihelion, when the orbit brings the comet closest to the sun, and the southern regions are exposed to an intense and prolonged burst of solar energy. Fact 69. The two hemispheres look different because of this. The southern side, blasted each perihelion, is rugged, scarred, and stripped of the fine dust layer that settles over quieter surfaces. The northern side is gentler, more covered in the dusty material that accumulates during the long, calm northern spring and summer. You can read the comet's seasons in its geography. Fact 70. The Hapy neck, the crack region, the narrowest and most stressed part of the duck, poured out some of the earliest and brightest jets as the comet warmed. The neck is where the two lobes are still weakly joined, where the growing fracture runs its 500 meters through the old ice, and it is also where the internal material is most accessible to sunlight. The same weakness that may eventually split the comet is what made it active first. On 13 August 2015, the comet reached perihelion. Fact 71. Rosetta was there. After 11 years of travel, launch, slingshots, hibernation, arrival, orbit, it watched 67P reach its closest point to the sun. At perihelion, the comet was about 186 million kilometers from the sun, roughly the distance at which Mars orbits, and it was at its most furious. Jets of gas and dust were erupting from dozens of active spots on the surface. The coma, the thin, glowing envelope of gas surrounding the nucleus, had expanded to enormous size. The comet's tail stretched away in the solar wind. The activity was intense enough to cause problems for Rosetta. The escaping dust, fine particles of comet material accelerated outward by the gas jets, was dense enough around the nucleus that the spacecraft's star trackers, the navigation instruments that orient it by recognizing the pattern of nearby stars, were being fooled. The dust grains, catching sunlight, were bright enough to be mistaken for stars. Controllers had to back Rosetta off to a safer distance, further from the nucleus, watching from further away while the comet burned at its most active. Each orbit, the comet loses part of itself. A layer of ice and dust is stripped away each perihelion, the material flying off into the inner solar system, eventually dispersing into space or settling elsewhere. Comets, like 67P, are mortal on a cosmic clock, shrinking fractionally with each return, slowly diminishing across the millions of years their orbits persist. The duck is slightly smaller than it was last orbit. It will be slightly smaller again next time. But something else was also happening in the space around the comet during this period of intense activity, something gentler and more surprising than the violence of the outgassing jets. Fact 86. The comet was wrapped in a faint ultraviolet aurora. Galland and colleagues, working with Rosetta data published in 2020, revealed that 67P was surrounded by a delicate aurora, not the green and red sheets of light that curl over Earth's poles, powered by energetic particles channeled by a planetary magnetic field, but something quieter and more diffuse. At 67P, which has no significant magnetic field of its own, the aurora formed as solar particles, electrons and ions streaming out from the sun, struck the comet's thin coma of gas and made it glow faintly in ultraviolet wavelengths. The comet's thin breath, its barely there atmosphere of water vapor and carbon dioxide and oxygen and organic molecules, was being lit from within by the collision of sunlight's charged companions. No instrument on Earth could have seen it directly. The aurora was too faint, too far, too deeply ultraviolet. Rosetta found it because it was there, in the coma, carrying instruments designed to measure exactly this kind of interaction. Another thing the comet was doing that it had always done, in all those billions of years of orbiting, quietly and invisibly, waiting for something to come close enough to notice. And through all of this, through the oxygen measurements and the glycine detection and the wrong water and the aurora and the perihelion and the singing and the dust fooling the star trackers, Rosetta was aging. All missions age. The spacecraft had been designed for a finite operational life. The mission had an end date, a terminal point built into the planning from the beginning, and as 2016 arrived, it was approaching. The question was how to spend the last of it. Fact 73. Rosetta ended its mission by landing on the comet on purpose. This is one of the most quietly remarkable decisions in the history of space exploration, and it deserves to be understood for what it was. When a mission ends, there are several options. A spacecraft can be left to drift in space, cold and silent, until orbital mechanics eventually dispose of it, or it simply becomes part of the interplanetary debris field. It can be commanded into a final trajectory away from anything interesting. It can be switched off remotely. The team at ESA chose something else. They decided that Rosetta should not simply stop operating. It should go down. It should descend to the surface of the comet it had spent years orbiting and studying, and it should touch that surface, and then it should be silent. The reasons were partly scientific. A descent would allow Rosetta to image the surface at very close range during the approach, capturing detail no orbital pass could match, and to take final measurements of the gas and dust at extremely low altitudes. But the reasons were also something harder to name. After 12 years of flight and 2 years of intimate companionship with this small black world, letting Rosetta simply drift away felt wrong. And there was the matter of Philae, resting somewhere in the shadows of Abydos, found only weeks before, in September 2016, its final location confirmed, but its condition permanent. The lander was there. Rosetta was there. The decision was made. Rosetta would come down. Fact 74. It fell at the pace of a slow walk. The final descent to the surface of 67P ended with a touch at about 90 centimeters per second. Not a crash, not an impact in any dramatic sense. 90 centimeters per second is a comfortable walking pace, the speed at which a person might cross a quiet room without hurrying, the speed of an unhurried hand reaching for something on a low shelf. Rosetta, a spacecraft the size of a large van with wings spanning 32 meters, touched the surface of a comet 4 billion kilometers from where it was built at the speed of a slow walk. Fact 75. It aimed for the Ma'at region near a pit informally called Deir el-Medina. Ma'at is named for the Egyptian goddess of truth, justice, and cosmic order. One of the Egyptian deities whose names had been scattered across the surface of 67P by the naming conventions of the mission, the Rosetta theme carried all the way to the landscape of the comet itself. The Deir el-Medina pit was chosen partly for scientific reasons. Its walls were thought to display the goosebump formations, those clustered 3-meter bumps believed to be the original pebble-sized cometesimals, the grains from which the whole comet was assembled 4.5 billion years ago. In its final approach, Rosetta would photograph what might be the oldest visible structures on the comet, the tiny primordial building blocks still sitting on the wall of a pit, waiting. Fact 76. It took pictures until the very last seconds. This is the part that is very hard to think about without feeling something. During the entire descent, hours of slow falling through that almost gravity, through the thin coma of gas and dust, past the boulders and the dune fields and the scarred southern cliffs toward the pit walls of Ma'at, Rosetta was sending back images. Its camera kept shooting. The last complete image was taken from an altitude of just about 20 meters, the surface filling the frame, the texture of the ancient material visible in extraordinary detail. Individual features resolving into the clearest pictures ever taken of the comet's skin. And then, just meters above the surface, contact. Fact 77. On touchdown, it fell silent forever. The spacecraft was designed to switch off on impact. There was no dramatic last transmission, no final sentence. The signal from Rosetta simply stopped. The last data were received at ESA's mission control in Darmstadt at 11 minutes and 19 seconds past 10 in the morning, Central European Time, on 30 September 2016. That was when the light carrying Rosetta's final signal arrived at Earth. The signal itself had left the comet about 28 minutes earlier, given the distance. The actual moment of touchdown had already happened, in silence, before anyone on Earth knew it. When the signal stopped, the mission was over, 12 years and 209 days after launch. 4.5 billion kilometers from home. On the surface of a 4-kilometer duck-shaped comet. Controllers wept, the images of the control room in those minutes, the people standing. Some covering their faces, some holding one another, some simply still, are among the most human photographs in the history of space exploration. Fact 78. Rosetta and Philae now rest on the same small world. The orbiter and its lander, built together, launched together, separated in orbit and reunited by accident and intention on the surface of the comet they had crossed the solar system to find. Philae in its shadowed crevice in Abydos, tilted on its side with one leg in the air. Rosetta somewhere in the Ma'at region near the Deir el-Medina pit, its final image frames containing the last view it ever had, both of them on 67p. Both of them dark and quiet, as the comet continues its 6.5-year arc through the solar system, as the sun warms and cools and warms them again, as the crack in the neck works its slow way through the ancient ice. The mission spanned more than a decade of active flight. Rosetta was launched in 2004 and came to rest in 2016, over 12 years of operation. It carried 11 instruments on the orbiter and 10 on the lander. Cameras and spectrometers and dust catchers and magnetometers, each designed for a specific set of questions about this one comet. It returned tens of thousands of images, enough to map 67p down to individual meter-scale boulders. Enough to build a full three-dimensional model of the comet, every crag and pit and cliff face accounted for, the most detailed model of any comet ever made. It was a mission of thousands of people across Europe and beyond. Scientists and engineers from many nations, built over decades, planned and replanned as the technology evolved, and the target comet turned out to be more interesting and more complex than anyone had imagined when they first chose it. ESA led it, with contributions from many countries and from NASA. The bill in human attention and effort, the accumulated hours of work and worry across the years, is simply not countable. And the comet? The comet continues. That is what keeps coming back, at the end of all the facts. The mission is over, the spacecraft are at rest, the data have been analyzed and the papers published, and the findings discussed and integrated, and sometimes contested and refined and discussed again. All of that is done, or ongoing in the way science is always ongoing. But the comet is not done. Fact 100. Somewhere out there the duck is still circling the sun. 67p Churyumov-Gerasimenko is still on its 6.5-year orbit, still swinging from its closest approach around the distance of Mars out to its farthest past Jupiter, into the cold. It completed another perihelion in November 2021. It will make another in early 2028, and another after that, and another, and the count will continue long after everyone who worked on Rosetta has grown old, and long after most of what we think we know about comets has been revised and sharpened by missions yet to fly. Each orbit takes a little more from it. The neck is wearing. The crack in the Hapy region is working its way through the ancient ice, grain by grain, orbit by orbit. The two lobes that gently fused in the deep past, slowly being pulled apart again by the strain of spinning and heating and cooling. One day, perhaps in thousands of years, perhaps in tens of thousands, the time scale is uncertain. The duck may split. The head and the body may drift apart on their own trajectories, two separate small comets where there was one, undoing the slow merger of 4.5 billion years ago. Two ancient bodies coming together and then eventually parting again on timescales that make human history look like an afternoon. Until then, the neck holds, and the comet sings, its 40 to 50 millihertz hum, inaudible to any ear, pulsing in the magnetic field around it as the solar wind moves through its coma. The song has been playing since before the Earth had oceans. It was playing when Churyumov noticed the unexpected smudge on Gerasimenko's photographic plate in Alma-Ata in September 1969. It was playing all the years between that discovery and the morning in 2004 when an Ariane 5 lifted off from Kourou and sent Rosetta on its 10-year chase. It was playing when Rosetta arrived, and when Philae fell, and when the harpoons failed, and when the little lander bounced a full kilometer into the black sky. It was playing at perihelion on 13 August 2015, when the jets were at their fiercest and the dust confused the star trackers, and the southern cliffs were eroding in the intense short summer. It was playing on 30 September 2016 when Rosetta descended at a walking pace toward the surface and fell silent. It is playing now. This is what you have been listening to, in a sense, through all these quiet facts. The history of a coal-black, 4-kilometer world that is mostly empty space, so porous it would float on water, darker than charcoal, shaped like a bath toy, made of two ancient bodies that drifted together at a walking pace and merged in the slowest possible collision. A world where you could step off the surface and sail away forever on a modest leap. Where the day is 12.5 hours and the year is 6.5 hours, where the surface temperature swings from deep freeze to just warm enough to turn ice directly to vapor, where boulders the size of houses sit on plains of dune like ripples shaped by invisible gas flows, where goosebump formations on cliff walls may be the original grains from which the whole thing was assembled. A world where molecular oxygen has been frozen in for 4.5 billion years, somehow surviving the chemistry that should have destroyed it. Where the simplest amino acid, glycine, drifts off in the thin gas of the coma alongside phosphorus, the backbone of DNA. Where the water is the wrong kind for Earth's oceans, heavier than what we drink, carrying a message in its deuterium ratio about where it formed and where Earth's oceans did not come from. Where noble gases, argon, krypton, xenon, preserve a frozen record of the cold conditions in which the comet was born, a sealed envelope that has not been opened in 4 billion years until Rosetta's instruments opened it. A world whose neck is cracking, whose two lobes may one day drift apart, which wraps itself in a faint ultraviolet aurora when solar particles strike its coma, which sheds some of its dust into brief orbit around itself before the grains fall back or escape, which triggered a boulder to move 140 meters over the course of Rosetta's watch, quietly rearranging its own surface while no one was looking. A world that carries, on its surface, the instruments of one spacecraft and the body of another, a nickel disk, etched with text in over 1,000 human languages, still attached to Rosetta's body, legible in principle, riding the duck through the dark. A testimony to the impulse that sent us out there. The belief that the question of where we come from is worth 10 years of travel, and 6 billion kilometers, and 32-meter solar wings, and 4 gravity slingshots, and a hibernation, and a wake-up, and a lost lander, and a deliberate, quiet, walking speed descent onto a surface that no one had ever touched before. The comet is about 4.5 billion years old. It has been doing this, circling, sublimating, singing, cracking slowly, for longer than the Earth has had a moon. It will be doing it long after any record of Rosetta remains readable to anyone. The mission was 12 years. The comet is 4.5 billion. Both of those numbers are true, and holding them together in the same thought is a way of feeling the scale of the thing, not with anxiety, but with something closer to wonder at the patience of the universe, the way it simply continues, the way the comet simply goes. Somewhere along the way, if you have been drifting, the facts may have loosened their grip on you. Fact 34 may have taken you part of the way under, the Hello World wake-up call from a spacecraft that had been silent and spinning for nearly 3 years in the dark. Or the first bounce, the kilometer-high drift for 2 hours over the surface of a world with almost no gravity. Or the song. The song has a way of doing it. 40 to 50 millihertz, sped up 10,000 times, clicking and warbling through the space around a comet that has been making that sound for billions of years without knowing it. Or the water, the wrong water, heavier than Earth's, carrying its message about where the oceans did not come from. Or the glycine, the simplest amino acid drifting in the thin gas around a comet. 4.5 billion years old, still intact, still recognizable, still one of the same molecules from which life is built. Or Rosetta, falling at the speed of a slow walk toward the surface, taking pictures to the last seconds. Or the image of the two of them, orbiter and lander, both at rest on the same small dark world, the mission over, the comet continuing. This is the kind of quiet the universe offers if you let yourself be still long enough to receive it. Not emptiness. There is very little emptiness out there, as it turns out. The space between the planets is full of charged particles and magnetic fields and dust and organic molecules and faint auroras and magnetic songs too low to hear. The comets carry amino acids. The ice preserves noble gases from before the planets formed. The duck is dark and porous and ancient and cracked and still circling. And Rosetta is there. And Philae is there, tilted in its shadowed crevice, one leg in the air, exactly as it landed after 3 gentle bounces on a comet 4 kilometers across and 4 billion years old. 97 more facts were told tonight, one quiet thing after another, the full count of 100 small true wonders about a rubber duck comet and the 10-year chase that found it. They are all still true in the dark. The comet's orbit has not changed because you heard about it. The crack in the neck has not paused. The inaudible song has not stopped. All of it continues, as it always has, as it always will, long after you and I and everyone who built Rosetta and named its regions after Egyptian gods and wept in the control room when the signal stopped. Long after all of that, the duck will still be out there, somewhere on its 6.5-year loop, wearing a little thinner each orbit, still carrying 2 quiet machines, still humming its inaudible hum in the dark. You can put that down now. You have heard all 100. You can let them drift. Good night from up here in orbit. I'll keep watch while you drift.